Metal structures like this golden crown or goblet here can trap light. Since the goblet is very smooth, it's not hard to imagine the light going round and round inside, forming electromagnetic modes. The objective of our research is to modulate light in vibrating goblets. If the goblet is very small, with sub-micron radius, then we call the electromagnetic modes plasmons, or more specifically, Mie-like plasmons, after the German scientist Gustav Mie. Violet? More goblets! Let's arrange them like this. Our sample is in fact a close-packed array of golden goblets, forming a plasmonic crystal. A section of the sample is shown here together with an electron microscope image. The truncated nanovoids intersect a bit, giving an interconnected structure marked by triangular pillars. Electromagnetic simulations, like this one for blue light, confirm that the light in Mie modes is concentrated inside the nanovoids. To produce vibrations, what we effectively do is take a hammer and strike the plasmonic crystal. These vibrations show that it's not just a plasmonic crystal, it's also a phononic crystal. Actually, instead of a hammer, we use ultra-short light pulses. In the experiment, red laser light pulses create tiny vibrations by heating a small submicron spot. Blue light pulses detect the vibrations through intensity changes at the same point. These are very high-pitched vibrations, around 1 gigahertz. We scan the sample position and change the timing of the laser pulses to make movies. Here is an example for a 6 micron square area. It is slowed down 1,000 million times. The intensity fluctuations are caused by the structure flexing. We process the data to extract the vibrational frequencies one by one, like this example at around 0.7 gigahertz, where we see a strong mechanical resonance. The hexagon encloses a region with 7 nanovoids. By averaging the data, we can form a good picture of where the vibrations are most efficiently generated and detected. Here you can see them very strongly at the center of the nanovoids at 3 different vibrational resonance frequencies. We can also watch the variation in time at these frequencies as movies. To understand these data, let's look at a numerical simulation corresponding to a hammer blow to the center of a nanovoid. This produces acoustic modes, analogous to the electromagnetic modes I already mentioned. This is a side view of the sample motion at around 1 gigahertz. You can see the central nanovoid periodically opening and closing. It's just like a golden goblet opening and closing. This breathing motion changes the nanovoid plasmonic resonances. We believe that the plasmonic response is enhancing the observed signals we detect from the void center. So we can map vibrations in a plasmonic phononic crystal. If you think that's a mouthful, you can say plasphonic crystal. Engineering both the plasmonic and phononic properties of our plasphonic crystal to enhance the optomechanical interactions could open up the possibility for novel devices such as high-frequency acousto-optic modulators. I shall conclude by drinking your health in a plasmonic void. Mead, Violet! A measure of mead! Cheers!